We're now going to begin talking about motion graphs in a little bit more of a concrete mathematical way. So there's basically three things that we're going to look at, three mathematical operations that we can do to a graph. And they are reading the graph, sloping the graph, and integrating. Now these two, reading and sloping, you're probably very familiar with. Reading is really just looking at the graph, sloping you've done before. Integrating it is actually a calculus thing, but we're going to learn a way to do it without really doing calculus, and we'll talk about that in a second. So we're going to review each of these, and then we're going to talk about how it applies to motion graphs. In the end, we want to be able to do all three, and also we want to know what the units are going to be for all three operations. The first and most basic one is reading the graph, and all we're doing here is just looking at the y-axis, okay, to see what values we have, usually for a given x value. All right. The units are simply going to be whatever the units are on the y-axis. And the meaning of it is we're getting a specific y value for a given x value. We have a quick example here. So we have this graph of student attention span versus days until the weekend. So when we read the graph, we're going to be looking at the values on the y-axis. All right. So if we want to know what the student attention span is when there are 2 days until the weekend, we're going to look here at 2 days, and we go over, and we see that the value on the y-axis is 8. So 8 minutes, right? So here is our y value for a given x value of 2 days. The next operation is sloping a graph. The way we find that, there's a few ways of doing it. I always go with this formula that slope is delta y over delta x, but a lot of times you'll also see it as rise over run, or actually written out the two changes, change in y, so y2 minus y1, over change in x, x2 minus x1. Any of those work, whatever you're most used to is fine. When we do the slope, first of all, the units are always going to be the units of the y-axis divided by the units of the x, and that simply comes from the formula. That's what we're going to be left with unit-wise. And what the slope really tells us, what the meaning of it is it tells us how quickly the y values change as the x values change. So it's really the rate of change of the y as a function of whatever is on the x-axis. For our motion graphs, it's going to be time. But that won't always be the case. Two things to keep in mind, just 2 important points. Number one, do not assume that 0, 0 is a point. Okay, when you're finding these slopes, sometimes that's an assumption that people make, and that's not always true. Sometimes it will be a point, but it won't always be a point. And the other thing is we want to take points that are far apart. All right, so try and use as much of the graph as possible. This is more true when we have lines that don't necessarily intersect perfectly on the graph, but it's always a good idea to just get into that habit. So we're going to go and work through a quick example here. So let's take some points here and find the slope. So I'm going to start with that first point there, which is 0, 2. And then I'm going to take this very, very end point here, which is 4, 14. And so to get my slope, it's going to be change in y over change in x. So that's going to leave me with 14 minus 2, my change in y, over 4 minus 0, or 3, and the units will be minutes per day. What that means is that the student's attention span will increase by 3 minutes for every additional day until the weekend. So it's the rate of change of the y as a function of the x. All right, this last one is integrating, and this is the one that you're probably not as familiar with, and we're going to spend a little bit more time working on it. So let's think about this example for a second. Suppose that a person walks at a constant speed of 3 meters per second for 5 seconds. How far did they walk? Well, we have a few ways of doing this. If we want to be very formal, we can say that that is their average speed, and that's going to be equal to distance over time. So we can say that 3 equals our distance over 5, which means our distance is simply 15 meters. Some of you might have just realized that you just multiply these two together and kind of skipped this more formal mathematical part, but the point is they're going to walk 15 meters, and the way we get that is by multiplying this velocity here by the time that they walk. So I'm going to look now at this graph that I have to the right, which is a motion graph showing that very motion, showing a person walking at a constant speed of 3 meters per second for 5 seconds. And here's my question. Is there a way that we can use the motion graph to get the same answer? Now keep in mind that we've simply multiplied the velocity by the time. We look here, here's our velocity of 3, here's our time of 5, so if we multiply them together, it's going to give us the time. But it also is going to be the area. It's going to be the area of that rectangle there, 3 by 5. And it's going to lead us to the same answer. Now, for something like this might seem like not a big deal. This might seem kind of worthless. However, there are going to be situations where we're not going to be able to simply multiply two numbers together. And this really comes up when we have situations where one of the values is changing. So maybe it's no longer a constant speed of 3 meters per second. It's no longer a horizontal line like we have here. And that's when integrating becomes really powerful. So let's talk for a second about the meaning of it, and then we'll talk about a few tips here. So integrating is another way of saying finding the area under the curve, or the area between the graph and the x-axis. That is what we're finding, that area when we integrate. If you're in calculus class, you're going to do this a lot more in depth. You're going to deal with curves and a lot of funky shapes. In our class, it's all going to end up being basic geometric shapes. They're going to make it easier to find that area without having to do full formal calculus. But what it really gets at, what it really does, as we were talking about on the last slide, is it gives us a special way of multiplying the x and the y axis. All right? And the reason why I say it's a special way is that it allows us to deal with situations when the value in the y is changing, when it's a non-constant y value. The units, since we're multiplying the y and the x-axis together, is simply going to be the x-axis times the y-axis. So let's take a look at an example here. We want to go ahead and find the integral, find the area from 1 day to 4 days. So this area here. Okay, so the first thing I'm going to do is I'm going to always shade in that area, the area between the line and the x-axis. And then I'm going to go ahead and think about how I can find that area. Now, you may recognize this shape here. It is a trapezoid. And maybe you remember the formula for the area of a trapezoid is 1/2 base 1 plus base 2 times height. But if you don't, that's quite alright, because we have another little trick we can do. We don't have to do that entire trapezoid. What we can do is we can focus on this rectangle first. I'm going to call that area 1. And then this triangle here, which I'm going to call area 2. So to find the area for area 1, that's simply base times height. So my base here is from 1 to 3, or from 1 to 4, which is a base of 3. My height here is going to be from 0 up to 5. So the area for that first part is going to be 15. Now I'm going to take a look at my triangle. The area for that is 1/2 base times height. So my base is also 3 from 1 all the way up to 4. My height is going to be from 5 up to 14, so that's a height of 9. Be careful, that height is not 14 because the triangle starts here at 5. And so I get the area 2 is going to be 13.5. So my total area here, I'm going to just bring both of these up here. When I add them together, is 28.5. And the units are going to be the units of the x-axis times the units of the y-axis, which is going to give me 28.5 minute days. A few quick tips here in terms of doing integration. So the first one we saw already, that you can always split up the area into multiple shapes and add up each area. That's really, really useful. Usually, I shouldn't say usually, always you're going to have shapes that can be split up into a series of triangles and rectangles. So use that to your advantage. I think most of us can remember, and it's also on your formula sheet, the area of a rectangle and the area of a triangle. You don't necessarily have to do it in terms of trapezoids, but you're certainly welcome to do that. The second tip to keep in mind, and this is really getting a little bit more into the meaning, is that the integral always tells us the change over a period of time or distance or whatever the x-axis is. Okay, so that one's a little bit more complicated mathematically, but keep in mind it's always giving you the change. So when we do integration of a velocity graph, it's going to give us the change in position, not the actual position. And the last thing to keep in mind, and we didn't see this in the example we did, but sections below the x-axis are going to have a negative area. And I realize that from a physical standpoint that doesn't make sense, but keep in mind that the area under the curve does not necessarily represent a physical area. It represents something else. It represents displacement or change in velocity or something. Okay, so it's okay for that to have a negative area. Alright, so let's bring this back to motion graphs specifically and think about the meaning of reading, sloping, and integrating the two types of graphs that we have. So let's start with the position versus time graph, and I'm just going to think right now about the units and then what that means. So if I read a position versus time graph, it's going to have units of meters. That is the unit of position. If I slope it, it's going to be y over x. That's going to have units of meters per second, which is going to represent velocity, and we've talked about that conceptually. If I integrate it, it's going to have units of meters times seconds, and maybe you know what that is, but I don't. But that is going to be nothing. All right, there is no meaning for integrating a position versus time graph. Moving on to our velocity graph. If we read it, we get units of meters per second, which is velocity. If we slope it, we get units of meters per second or meters per second squared, which, as we know from conceptual discussions before, represents our acceleration. And if we integrate it, we get units of meters per second times seconds, or just meters, which is the units for position. But remember what we said, when we integrate, it gives us the change always. So this is going to be the change in position. And so here we have a table just summarizing what we just talked about. For each graph of reading it, sloping, and integrating it, this shows what quantity we get from doing that piece of analysis. One thing I just briefly like to point out here, and maybe you notice this, when we have a position versus time graph and we take the slope of it, it gives us velocity. We have a velocity versus time graph, we take the slope of that, it gives us acceleration. We actually could continue going on with this, and if we took the slope of a velocity acceleration versus time, it would give us jerk. Take the slope of that, it gives us jounce. And we could continue going. Jerk and jounce are absolutely real physics terms. Allegedly, the next three, taking the slope each time, are snap, crackle, and pop, but the sources on those are not quite as legitimate. Going the other way, starting with a velocity versus time graph, if we integrate it, it gives us a change in position, and similarly, if we had an acceleration versus time graph, if we integrated that, it would give us the change in velocity.